Good morning, class. We are looking at algebra practice test number 3. For module 3, covering chapters 5 and 6, here's chapter 6, exponential and logarithmic functions. We've done a big chunk of it. Here's the second part. And reminding you of the general logarithmic properties when y is log x base b, that is equivalent to, say, b to the power of y equals x. And it gives several properties you have seen previously. I hope you're comfortable with that. Now we want to expand each log. Part A, log base 7 of x, y, z. So we are going to use number 5, which is the product rule. It becomes log x plus log y plus log z, and all of them have the same base, 7. Same base. Part B, ln of 9 over x uses number 6, the quotient rule. Ln of the numerator 9 minus ln of the denominator x. That is known as the quotient rule. Part C, we're going to use the power rule and put the power in front. Log of y to the power of 10 becomes 10 log y. Now, part D, we're going to combine all of those. So first, we have a fraction, so log of the numerator minus the log of the denominator. That is the quotient rule, everybody. In other words, number 6. Then we are going to separate this one into log a squared plus log b to the power of 4. Both of them have the same base, namely x. This is using number 5, the product rule. And now in each case, we are going to use the last rule, the power rule. We put the 2 in front, 4 in front, 7 in front, becomes 2 log base x of a plus 4 log base x of b minus 7 log base x of c. Expand. Well, you're going to continue with the same concept, decomposition of a log, and we notice this can be written as the same expression to the power of 1/2. Using number 7, we can put this in front, becomes 1/2 of log x cubed with the y to the power of 5. So we put the 1/2 in front. And then this uses number 5. The product rule becomes log of x cubed plus log of y to the power of 5. And again, remember, 1/2 sits in front. Now this to follow number 7, and we can bring the 3 in front, 5 in front, and we're going to multiply each one by 1/2. We get 3 halves log x plus 5 halves log y. Part B, ln of x over x squared plus y squared. We are going to use number 6, the quotient rule. ln of the top minus ln of the bottom becomes ln x minus ln of parentheses x squared plus y squared. Part C, log base 4 of square root of x times cube root of 10y over z to the power of 10. Please understand, when you have enough experience, you can do this actually in one shot, but we are going to do it in a few steps. Number one, we are going to go with number 6, the quotient rule. Log base 4 of the top minus log base 4 of the bottom, which means log base 4 of square root of x cube root of 10y minus log base 4 of z to the power of 10. This is practically done. Let's work on this by writing this as x to the power of 1/2, 10y to the power of 1/3. So all we are working on, we are changing this to this format, changing this to this format. And there is a reason, on purpose, I want to put a raised dot in between just to mention that is going to use number 5, the product rule, to be separated into two pieces. Log base 4 of this one plus log base 4 of the second piece. And we're not going to touch the last piece yet. So this becomes log base 4 of x to the power of 1/2 plus log base 4 of 10y to the power of 1/3 minus log base 4 of z to the power of 10. Now, 1/2 can sit in front, 1/3 can sit in front, 10 can sit in front as we use the power rule. So specifically for this one, I want to do that first because now 10y can be separated into 10 times y. So log base 4 of 10 plus log base 4 of y. So just this part. So this one, you put the 1/2 in front, you put the 10 in front. So notice what happens. You get 1/2 log base 4 of x. This one, 1/3 log base 4 of 10 plus log base 4 of y. Remember, the 1/3 is being multiplied by both. And this one, 10 sits in front, and we are done. Completely decomposed. So the final answer for this guy is 1/2 of log x base 4 plus 1/3 log base 4 of 10 plus 1/3 log base 4 of y minus 10 log base 4 of z. You have to mention the base somehow, somewhere. Now, let's combine them into a single log or condense them. Either way, it depends on how they use the word. So if you look at this one, we are going to go back to number 5, but this time, instead of going from left to right, we're going to go from right to left. So this time, we go this way. So this simply put becomes log of the product of these two expressions, which is log of 6x to the power of 9. For part B, we're going to use number 6, and we're going to go from right to left. It becomes ln of 6x to the power of 9 over x squared. And we get ln of 6x to the power of 7. So that's very straightforward, everybody. All right, let's look at more examples now. We do this in a couple of steps. And again, in this case, let me use a different color. We are going to use this one. So we're going to put the 2 up here. We're going to put the 3 up here. So the reverse process of the power rule. That's the first step. The second step is to go back to number 5. The product rule, the reverse process means multiply the 2. So log of x squared times x plus 1 cubed. And what I want to make a point of here, as far as I'm concerned, this is perfect answer and you're done. In some instances, they may want you to multiply them out, okay? If so, then just follow what they're asking you to do. Again, like I said, to me, it's not that big of a deal, okay? But in some cases, they may make it a big deal and you want to follow that to be on the safe side. What happens here is that we notice this one and this one have the same sign. That means a plus sign. And we can put them next to each other. This one has a negative sign. We put the 1/2 here. Again, we are looking at number 7, the reverse process of number 7. And what happens, we do write log x plus 3 log z, and 3 log z also, let me do that. I put it here. So I'm going to write log x plus log z cubed minus log of y to the power of 1/2 is square root of y. And so we can combine these two into log, and we can do it in 2 shots, although it can be done in 1. These 2 into log x z cubed minus log of square root of y. And now we are going to go back to number 6, everybody. Again, the reverse process. Log, of course, we don't write the base because there is no base. That means the base is 10 of xz cubed over square root of y. That is the final answer. So I hope it's pretty straightforward, everybody. So sometimes we go from left to right, sometimes we go from right to left. Again, that is easy to understand as long as we are comfortable with the concept of logarithmic properties, everybody. Logarithmic properties. Back and forth. We want to solve equations. The first one is 5 to the power of minus 4x minus 3 equals 5 to the power of minus x. So a couple of properties. If a to the power of x equals a to the power of y, that means they have the same base, they must have the same exponent. Or if a to the power of x and b to the power of x is the same, meaning they have the same exponent, they must have the same base. In this case, we have the same base. So the exponents must be the same. I can move this one this way. I get plus x, move this one, and divide both sides by -3. X becomes -1. As always, you can put it back into the original equation to check your 64 times 4 to the power of 3x equals 60. What happens with a case like this? Well, we want to come up with the same base. And we notice 64 is 4 cubed, 16 is 4 squared. Now we can see that we have the same base on both sides, 4. So the right side is fine. The left side, we're going to combine them by adding the exponents. This is the product rule. 4 to the power of 3 plus 3x is the left side. Now the left and right have the same base. They must have the same exponent. So 3 plus 3x must be equal to 2. We move the 3 becomes negative, subtracted from 2 is -1 divided by 3, x becomes -1/3. So pretty straightforward, everybody. Two times e to the power of 3x equals 13. We're going to divide both sides by 2. And in order to get to the exponent anywhere, anytime you have an exponential and you want to solve for the exponent, you have to take a log of both sides. On the left side, we have the base e. Because the base is e, we take a natural log. Let's say the base was 10, we would take a common log. If it's other than that, any log will do, and we choose one of them. The left side is simply 3x. Divide by 3. So x becomes 1/3 of ln of 13/2. This, everybody, is an exact answer. And normally we want to answer exact. If they ask you for an approximation, you put it into a calculator and however many decimals. This is an approximation with 1, 2, 3, 4, 5 decimals. When they say 5, you go to the sixth one to make a decision. So it's important to know what you have to do, okay? Now, to do this equation, you have two choices. You can go by substitution if you let e to the power of x, for example, be any variable of your choice. Of course, except x. Let's say this is y. Then this is y squared. And I have a feeling you have no problem factoring this. You want two numbers, the product is -6, the sum is -1, would be -3, +2. Some of you may not need that. You can factor it just the way it is. So you could write it as e to the power of x minus 3 times e to the power of x plus 2. Either way is fine. If you go this route, y is 3, y is -2. If you go this route, e to the power of x is 3, e to the power of x is -2. In either case, you have to go from there to here. So this one, you say y is 3, and you go to this one. This one, you say y equals -2. You go to this one because you have to change it. And now you want to solve for x. And remember, to do that, you take a natural log of both sides. Let me use a different color. So if I take the natural log of the left side becomes x. Okay. And I get x equals ln 3. And we can write the approximation. This cannot be. The reason it can't be, if you recall when you graph exponential functions, they are above the x-axis, meaning the range is from 0 to infinity. 0 is not included, so it can never be a negative number. So you want to be careful with that, okay? So it can't be a negative number, everybody. So the answer is ln 3 precisely. A rough estimate, again, they ask you to use a calculator, however many decimals, roughly 1.0986 or 1.1 again. How many decimals? It depends. We want to continue solving equations involving logs and exponentials. Log base 3 of 9k equals 2. Remember the general format. As far as logarithmic equations, if x equals y, log x and log y with any base must be the same. Bear in mind, x and y must be positive. The arguments must be positive. The base must be positive, in this case a, and can't be a 1. If we have log x base a and log x base b, because we have the same argument, we must have the same base. Okay, again, all bases, all arguments must be positive, and the bases can't be 1 either. So with that being the case, if we stick with that, if you have a log on one side, number on the other, you have to go with the definition of a log. So that means 9k must be 3 squared. And of course, 3 squared is 9. And k becomes 1. And it's important when you have logarithmic equations, you check, make sure none of the arguments become negative. Log 4 plus log of minus 5x equals 2. Notice both of them have the same base, and they must, and the base is 10, so you can combine it. Using the product rule, look at this one, number 5, we're going to go from right to left. So it's log of 4 times minus 5x, which makes it log of negative 20x. And now we're going to go with the definition with this arrow. Remember, we don't have a base and we have log. That means it's a common log, and that means the base must be 10. So minus 20x is 10 squared. What is 10 squared? 100. Divide both sides by negative 20, x becomes negative 5. Log base 7 of 5n minus 2 equals log base 7 of 8 minus 5n. Again, you have logs on both sides. You have a single log. Each side has the same base 7. They must have the same argument. So the argument 5n minus 2 and the argument 8 minus 5n must be the same. So we move things around as follows. We move this one this way, becomes plus 5, and this becomes plus 2, and 10n equals 10. Divide by 10, and becomes 1, and we are done. Now, again, we have logs on both sides. If you have logs and nothing else, you bring every side to a single log. The left side is done, but the right side, we can use the product rule, move it from right to left, meaning combine these two into 12 times x. The left side, you don't have to do anything. They have the same base, namely 10, because the base is missing. The base is 10 when you have log. They must have the same argument. X plus 12 must be equal to 12x. If I subtract this from here, I get 11x. And so x is 12 over 11 as the final answer. All right, whether we have a natural log, common log, or a general case makes no difference. The methodology is the same, everybody. If you have logs on one side, if you have logs on both sides, you have to bring each side into a single log. And again, it doesn't matter if it's a general log or a natural log. So the left side, we use number 6, the quotient rule, and we make it ln of x plus 4 over x. The right side, we don't have to do anything because it's a single log. Since they have the same base, they must have the same argument. And we do cross product. The product of these two is x plus 4. The product of these two is x squared plus x. I don't have to move things around. I notice I can drop the x from both sides. If x squared is 4, x has two answers, positive and negative 2. Now, when I go to the original equation, if I put 2, 2 plus 4, 2, 2, everything is fine. But if I put negative 2 here, this is not a problem because negative 2 plus 4 is positive 2. But this creates a problem. I don't even have to check this. This gives me a hard time. This is out. One solution only, x equals 2. What happens when you have a bunch of logs and numbers? Then every piece of log should come to the same side. Let's say there was another log here, we would move it to the left. And there was another number here, we would put it to the right. So separate the numbers from the logs. We don't have to do it here, it's already done. Logs are one side, number on the other. So we combine the logs, in this case using number 5, the product rule, into a single log, log base 2 of x times x minus 1. And now we go with the definition of a log and change it to an exponential format. Again, following this arrow, which means the argument is 2 to the power of 1. So x times x minus 1 is 2 to the power of 1. So again, your first step is to bring all the logs to a single log, bring all the numbers together, and then you use the definition of a log to change it to an exponential format. This becomes x squared minus x. You move the 2, make it negative, and that's an easy factoring. You want two numbers. The product is negative 2. The sum is negative 1. So x minus 2x plus 1. So x is either 2 or negative 1. And again, you check. When I put 2 here is fine. 2 minus 1 is positive is fine. I'm fine. If I put negative 1 here, doesn't work. I don't have to check any further. Negative 1 is out. If it doesn't work with one statement, one expression is out. Four to the power of x plus 10 equals 3. We want to solve this. And the very first thing we do is to move the 10, make it negative. 3 minus 10 becomes negative 7. And I hope you realize there is no solution because an exponential, remember, the range is from 0 to infinity, can never be negative. Okay, it can't even be 0. Now, One easy way to look at part B is to notice the right side is 1, and 1 can be 5 to the power of 0, 10 to the power of 0, or better yet, use the same base 7 to the power of 0. So what base do you use? The base that you need, the base that is given. So if they have the same base, they must have the same argument. X minus 10 must be 0, and obviously x is 10. So it's very straightforward, everybody. Four to the power of x is 9 to the power of x minus 2. And to solve that, we want to come up with the same base. We can't. So for 4 and 9, there is no way to come up with the same base. In this case, I have to take a log. Because I have to take the log, I look at the base. If any of them is e, I take a natural log. If any of them is 10, I take a common log. Because it's none of the above, it makes no difference if you go with ln or log, natural log or common log. So take a natural log of both sides. According to number 7, the exponent sits in front if we want to decompose the log. So x sits in front, in this case, x minus 2. And by the way, please understand ln4 is some number. If you use a calculator, it's a bunch of decimals. It looks ugly. You just follow that, and if need be, at the end, you can put it into a calculator. But for now, x ln4, x minus 2 ln9. All right. Distribute. Please understand you can distribute ln9. You get x times ln9 minus 2 times ln. Remember what you're doing. You are solving for x, everybody. Therefore, we are moving things around such that all the x's come together, the numbers to the other side. So we can do the following. Move this one this way, becomes positive. Move this one this way, becomes negative. Now, on the right side, I can factor the x out. All right. On the right side, I can take the x out and I get x times ln9 minus ln4. Please understand, ln9 minus ln4, those are all numbers. So all we have to do, divide both sides by ln9 minus ln4, and we get this answer, which is an exact answer, everybody. If you put it into a calculator, it gives you roughly 2.165. That's an approximation, class. And again, you don't want an approximation unless they ask you. I can't emphasize this enough, okay? Don't use approximation unless you're asked, in which case, as I mentioned, it becomes 2.165. Again, it depends on how many decimals they ask you, class, okay? That's important to understand. I just put a few, okay? But you always want to pay attention to how many they ask you. We want to find log base b of 50, where log base b of 2 is a, log base b of 3 is b, and log base b of 5 is c. To evaluate this, we have to cut this into formats that is factored form involving these numbers. You may recognize 50 is 2 times 25, and therefore is 2 times 5 squared. If you don't recognize that, you have to do the following, everybody. Factor. Remember the prime numbers. 2, 3, 5, 7, 11, 13, 17, and so forth. So you divide by the very first one that you can. Because 50 is an even number, is divisible by 2, 25. Can you divide by 2 anymore? No. Can you divide by next number 3? No. Can you divide by 5? Yes. 5, 5, 1. When you hit 1, you are done. So that's how you get log base 2, log base b of 2 times 5 squared. So you use number 5, the product rule, and you make it log 2 plus log 5 squared. Both of them have the same base b. And in this case, you put the 2 in front using number 7. And now you replace this one with a and this one with c, so you get a plus 2c as the final answer. Again, pretty straightforward. We look at the second part of this question. Where we are interested in finding log base b of the 5th root of 300, everybody. Well, first and foremost, we are going to write the fifth root of 300 as 300 to the power of 1/5. Then we are going to look at number 7 and say, okay, we're going to use the power rule and we put the 1/5 in front. Now we are almost there. We have to decompose 300. You may recognize this as 2 squared times 3 times 5 squared. I will go over the factoring, but then I also give you the easy way out. So hopefully you remember it from algebra. So here's what we do with 300. You start with 2, 150, 2, 75. First you go with 3, not 5. You go in order. You get 25, 5. You get 5. Divide by 5 is 1. And look at this one. This is a 2 squared times 3 times 5 squared. Now, one easy way, perhaps they have shown you a 0, which in essence means 10 is 2 times 5. Okay, you have 2 zeros, so you have 2 squared and 5 squared, and then the 3. You should be able to do that in your head again, if in case it was taught. Okay, now we are going to decompose this using the product rule and the power rule at the same time. First of all, this is log base b of 2 squared plus log base b of 3 plus log base b of 5 squared. Then this 2 sits in front for this one. 3 doesn't have anything. 5 has this. So I'm assuming by now you can do this in one shot. If you can't do it in one shot, take more steps. So this one gives you 2 log 2 base b. This one gives you simply log 3 base b. And this one gives you 2 log 5 base b. And so you replace it with ABC accordingly. The final answer would be 1/5 times 2a plus b plus 2c as the final answer. A nuclear reactor contains 200 grams of radioactive plutonium-239. Plutonium decays according to this formula. A equals a sub 0 e to the power of negative 0.0000284 T. How much will remain after 5,000 years? Find the half-life of plutonium. So a couple of things I want to explain. We have the exponential growth, and now we have the exponential decay. Exponential growth, that means it grows, and with that we have doubling time, how long it takes for it to double. And we have the half-life, that means however many grams or an investment that you have, how long does it take to go to half of its original size? That's the concept of a half-life. But anyways, going back to this, let's see what is going on. So it contains 200 grams to begin with. That means a sub 0 is 200 grams and T is 5,000 for this part. Plug in, replace the a sub 0, replace the T. So 200 e to the power of the product of these two numbers is negative 0.142. You raise e to that power times 200. Becomes 173.52. It's important to know this is because of these negatives, and it's an exponential decay, and it must go down. Now, as far as the half-life, I want to solve for the half-life in general for this case. And that means it doesn't matter if we have 200 grams or not. So I'm going to work with this equation. And the concept of a half-life, that means this becomes half of the original size, half of a sub 0. That's the meaning of it, everybody. The reason it doesn't matter what the original size is, 200 grams in this case, or any other number, it makes no difference because they cancel out. And since I want to solve for t, and this has a base e, and I want to take a log, specifically, I'm going to take a natural log of both sides. Again, why natural log? Because the base is e on one side. On the left side is ln 1 minus ln 2, and the right side just becomes that. We should know that ln1 is 0. So t is negative ln2 divided by negative 0.0000284. And if you plug it in, it becomes 24,406.59 years. It takes that long to go to half of the original size. Whatever that is, it happened to be 200 grams, it goes to 100 grams. So what I want to add is a couple of things. Number one, the continuous rate of growth is R or K. It depends. In some formulas, we use R. In some formulas, we use K. It means the same thing, everybody, okay? And K is the number that you see here without the negative sign. The continuous rate of growth for growth. For decay, we use minus R, so negative of that, no matter what, makes it the positive side. In other words, this number, we mention it as growth, and we use a positive for exponential growth. We mention it as decay, and we use negative for the decay. That's the concept that we need to know, okay? If we were to find the half-life in general, everybody, for this one becomes half of n sub 0 was n sub 0 e to the power minus kt. Just to let you know how that works, is to cancel each other. So if I take the natural log of the left side and natural log of the right side, the left side ln1 minus ln2 becomes minus ln2. The right side becomes minus kt. So I want you to pay attention to this because it gives you two formulas. I can solve for t, and I get ln2 divided by k. Negative cancels out negative. This is how you calculate the half-life, and I hope if you go back to the exponential growth, you remember you basically use the same formula, because sometimes you're looking for t. Sometimes you're looking for k. If the half-life is given, the rate k here is ln2 divided by the half-life, and you should be comfortable with both cases.